Welcome to Calculus. Today we will investigate finding critical numbers of functions over their entire domain. Take a look at three examples, and we need to decide first of all what is a critical number or a critical point of a function. So let's make that definition first. A critical point is given by this type of definition. So what we would say is a number C in the domain of F is a critical point if one of two things occurs. So it's a critical point if the value of the derivative, so we would write that as f prime at C equals 0. So that's one instance where I could identify a critical point if the value of the derivative evaluated at C equals 0, or if the value of the derivative at C does not exist. And so there's two possibilities for deciding whether or not I have a critical point at a certain domain value C. Either the value of the derivative at that C value equals 0, or the derivative at C doesn't exist. Well, in either case, I need to start by taking the derivative. So as I look at the first example here, f of x equals x cubed minus 6x. To find a critical point, I always want to start by taking the derivative. So for this polynomial, the derivative of f of x is going to be 3x squared minus 6. Now, once I take the derivative, in order to identify or locate any critical points, I do need to set that derivative function equal to 0 and then solve that equation. So I need to solve that now. So I'll begin. I notice that I've got a factor of 3 in both 3x squared and minus 6. So I'm going to divide that 3 out. And that'll give me x squared minus 2 equals 0. So here I've got really a quadratic equation that's missing its linear term. So if you see that instance, you can take the approach of moving the constant to the far side and then taking the square root. So I got x squared now equals positive 2. Take the square root of both sides. That'll reduce it down to just x on the left. And we're going to have two versions of this square root of 2 on the right. It's either going to be positive square root of 2 or negative square root of 2. And so what we're seeing with this function is that we should have two critical points. So over here we'll write our answer, critical points. So x equals, and we'll put it in a set, negative square root of 2, comma, positive square root of 2. Just to illustrate how that's showing up in the function of this f of x, let's just consider what the original graph looks like. So if I were to graph this function, it would be a cubic function that has the quality of a maximum on the left, a minimum on the right. So I'm just going to give a rough sketch of this graph. We'll go through the origin. And what we're seeing is that the two critical points we found are at these x values of negative square root of 2 and positive square root of 2. And so really what we're describing with these critical points, if we go up to the function, is where is the tangent line equal to 0. So definitely on that left-hand maximum at the x value of negative square root of 2, we have a maximum. And then on the right, we've got at x equals square root of 2, a minimum. And that completes that example. We found our two critical points for this f of x equals x cubed minus 6x. So that first example was a polynomial function. Let's also take a look at a rational function. Here we've got f of x equals x squared over x minus 1. So I want to start off like we did on our previous example, just by finding the derivative of the function. So I'm going to look for f prime of x, and since this is set up as a quotient, I'm going to use my quotient rule. So remember, this is considering f over g, and using quotient rule, it starts with g, so it's x minus 1 times the derivative of f, which is going to be 2x, minus just the original f, which is x squared, times the derivative of g, which in this case is just 1. And then it's all over g squared, so x minus 1 squared. So we'll clean that up to see what this is simplified for the derivative. So here x minus 1 times 2x, if I distribute the 2x, that's 2x squared minus 2x, and then minus x squared. And then I'll leave this undistributed in the denominator, x minus 1 squared. And then I've got like terms, 2x squared minus x squared. So that's going to be this final reduced form, x squared minus 2x all over x minus 1 squared. So just like we did in the previous example, I want to set that derivative equal to 0, and then I want to solve. Now, with a rational function, remember there's two things to consider here. The function itself is going to equal 0 when the numerator equals 0. So I'm going to take and set this equation, kind of make a separate but associated equation, x squared minus 2x equals 0. And then I want to solve that, because again, for the rational derivative here, it'll equal 0 when the numerator equals 0. So I'll solve this as a quadratic by factoring. This is x times x minus 2 equals 0. And then I'm going to take each of these factors, set them independently equal to 0. So immediately I have the value x equals 0. And if I take x minus 2, set it equal to 0, add 2 to both sides, I get x equals 2. So there's two places, two x values, c values, according to our definition for critical points, where the derivative will equal 0. It's at 0 and 2. But there's one more value that I have to consider for this function. It's the place where the derivative does not exist. So that would have to do with the denominator of the derivative. And really the idea there is I also want to set that x minus 1 equal to 0, x minus 1 squared equal to 0, and solve. That wouldn't be a point where the derivative equals 0, is a point where the derivative does not exist, because on the original function it would have been undefined. So let's locate that as well. Take the denominator, x minus 1 squared equal to 0. I could take square root of both sides to cancel the square. That's going to be x minus 1 equals 0. Add 1 over. And our third critical point here, which is a place where the derivative does not exist, is at x equals 1. So let's finalize our answer and then just take a quick look at the graph to see what features do these critical points describe. So we'll put this in a set to begin. So we got 0, 1, and 2. We'll box that. Those are my critical points. But again, I want to just see on the graph how these critical points are showing up. So for the original function, if I were to graph f of x equals x squared over x minus 1, this is a rational function. Because the power is higher in numerator than in the denominator, it's got a slant asymptote. So recall, to find the equation for slant asymptote, you would do polynomial long division, x squared divided by x minus 1. And if I did that out, I would put placeholders plus 0, x plus 0. I would get x plus 1. So that gives me this slant asymptote. And then I have a vertical asymptote. We've really found it already in our critical points. It's this value of 1 where the derivative does not exist. That's a vertical asymptote. So you can kind of see that's how that type of critical point would look on the original function. And then the graph itself, if I were to graph this, it would rise up under the slant asymptote, attain a maximum at 0, 0. And that 0 is that left-hand critical point. It would indicate an absolute maximum. And then to the right at 2, I would also have a critical point, and that one would indicate a relative minimum. And so we see like there's a variety of features on the original function that could indicate, like, hey, I got a critical point here. Again, by the definition, either you have the derivative equals 0, as at 0 and 2 here, or the derivative at the number does not exist, which is equivalent to our value here at positive 1. Well, we've taken a look at a polynomial function, a rational function. Let's take a look at a piecewise function. So here I've got f of x. It's defined as 2 linear parts, and it's really a restricted domain. It's defined as 3x from 0 to 1, inclusive of 0, not including 1, and then as 4 minus x from 1 up to 2. Now, let's take a look at the graph of this function. It's probably simpler just to look at the graph and then interpret about the derivatives from the graph. So we'll just graph from 0 to 1. In fact, let's make our scale a little bigger so we can catch points. So there's our extended domain there, 1, 2, 3. So if I were to graph this at 0, this function would be at 0. And then at 1, it would be at 3. So this left-hand piece of the piecewise function would be that red segment. And in fact, what I need to make sure to include is an open point here at 1, since it doesn't have the equals bar for the 1. And then the second part of the function does pick up, so 4 minus 1 is actually 3, so it's continuous. And then 4 minus 2 is going to be 2. And that's a graph of our function. So really what we need to decide is there a point on this graph where the derivative equals 0? Is there a point on the graph where the derivative does not exist? So as we look at that graph, there really is no place where that we could say, hey, we have an absolute maximum. We do have this point here, but that is not differentiable. Remember, one of the criteria for differentiability, although it is continuous at x equals 1, the value of the derivative on the left does not equal the value of the derivative on the right. So therefore, we would say that's not differentiable at x equals 1. So there's really not a point where the value of the derivative would equal 0. But I do have that single value at 1 where the derivative does not exist. And so what you would say for this example is that our critical point is at the x value of 1, not because there's a differentiable value of the function there, but because it doesn't exist. Well, thank you for joining for this investigation of finding critical points by taking the derivative and then looking for where does the derivative either equal 0 or not exist at all. Thanks for joining. See you soon.